Okay, so today we will go over this chapter 6 review worksheet. So forum 6 is review for the integration part of the last exam, and now is the other half of the exam. Okay, so 6.2 is areas bounded by curves, and 6.3, 6.4, they are on volumes. And 6.3 has two different types, right? One is on cross-sectional and the other one on solid of revolution, Washer method. So when you do the problems on the exam, you have to think carefully, right? So it's not all about finding volumes. Some problems may be on areas, right? And it's not all about finding volumes of solid of revolution, right? Because 6.3 have a half of the content is on cross-sectional method. So read the instruction carefully. Okay, so let's look at the three regions. Okay, so region 1 is bounded by the line 3 minus x, the curve 2 square root of x, and y-axis. Region 2 is bounded by 2 square root of x, 3 minus x, and the x-axis. And then region 3 is bounded by 2 square root of x, 3 minus x, and the vertical line x is 3. So we're gonna use these three regions throughout the entire worksheet, but we're doing different types of problems. Okay, so first, let's find the area of region number 1 in the x direction. Okay, so we're gonna integrate it with respect to x. So remember the setup, right, is to partition the x-axis, the interval on the x-axis from left to right. And then for each subinterval, you find a sample point, generate the rectangle. So the height of the rectangle, right, times the length of the subinterval, that gave you the area of a rectangle, right? If you remember this setup, you have a vertical rectangle. How do you find the height? So that will help you to remember what to look for because we have to find the height. So we draw a vertical segment, right? A typical one to help you focus. Okay, but you kind of want to eyeball it throughout the entire region. It's like you want to slide this vertical segment throughout the entire region. See if it always, right, the top part always sets on 3 minus x and the bottom always uh, sits on 2 square root of x. If that's the case, you do it in one integral. But if top or bottom changes, then you got to do it in two integrals, right? So imagine you're sliding the segment throughout the entire region. Number one, the top is always that green function, 3 minus x. The bottom is always the curve, 2 square root of x. So that indicates we can achieve that using one integral because you only need one formula to find the height. The intersection here, that's 1 comma 2. Okay, so we go from left to right. So left x coordinate, it's on the y-axis, so it's 0. Right, we stop at 1. That's the intersection. The x coordinate is 1. Top minus the bottom, top is 3 minus x minus the bottom. Bottom is 2 square root of x. And remember to finish up with dx or dy accordingly to complete the integral. Right, it's the height times the width, so don't drop the width of the rectangle. Okay, so that's number one. Number two, we want to find the same area, but this time we want to do it in terms of y. Right. So you gotta remember when we do it in the y direction, the variable is y, so we partition the interval along the y-axis. Right, same thing, we find sample point of subinterval, we generate the rectangle, but this time the rectangle is the horizontal kind. Right, the height is the length of the subinterval, delta y, and the length going from, between the functions, going through the region. Okay, so from the left, that's the y-axis, to the right, and you can see clearly we cannot do it using one formula because the lower portion left from the y-axis right to the curve to square root of x. The top portion will go from the y-axis to the line 3 minus x. So clearly we gotta do it with two integrals. And because we're doing in the y direction, there's one more thing that we have to do is to solve for those functions in terms of y. So y is 3 minus x, then x is 3 minus y. And y is 2 square root of x, then square root of x is y over 2. So x is y squared over 4. So to find the area of region number 1, the first integral will go from the bottom, 0, all the way up to the intersection over there. That's 2, because you look for the y-coordinate now. So this lower portion, function to the right is the curve, right? 2 square root of x. To the left, it's all the way to the y-axis. So basically, x is 0. And that's the typical interpretation of definite integral, right? It's bounded by curve and the y-axis. So it's just the function itself. Because if you think about how do you find the length, you subtract 0, right? So it's the same principle, it's just that this is the special case. But remember, we're gonna do it in terms of y, right? So that is y squared over 4. And remember to write dy. And the top portion will go from 2 all the way to 3. And that's the straight line part. So that's 3 minus y dy. Okay, so remember to write dy for each integral. So on the test, it's about communicating that you know the concept, right? That's not the time to omit things or not doing it properly because you don't like to do it or something. Okay, so keep in mind you want to clearly communicate that you know the concept. That's the key, right? The more you show me that you know, the more points that you get, right? If you skip steps, not communicating how you get the answer, it's like you try to hide something because I have no way of knowing how you get the answer. Maybe you know, or maybe you Googled it. I have no way to tell it. That's why it's your responsibility to communicate to me how you get the answer. Because if you know how to get it, it's no big deal. Okay, so it's super important, even for the little details, right? So don't omit the DY part. Okay, number 3. Now our focus is on region number 2. That's the bottom one. We want to find the area of region number 2 with respect to x. Okay, so with respect to x, the rectangles are vertical kind, and we need to find the height of the rectangles. As you can see that on the left-hand side, it goes from the curve to square root of x all the way to the x-axis, but toward the right side, it goes from the line 3 minus x all the way to the x-axis. So we cannot do it in one integral. We have to break it up and do it in two integrals. So this time the area goes from left 0. First stopping point is 1. So that's the left portion of the region. And this time we have 2 square root of x because it's just the area bounded by curve and the x-axis. Okay, it's just typical definition, definite integral of the function on that interval. Okay, so it's the region bounded by curve and the x-axis on the interval from 0 to 1. But if you can also think of how do you find the height, top minus the bottom. The top is 2 square root of x, the bottom y is 0, right? So, and we don't write minus 0. The second integral goes from 1 all the way to the right end, which is 3. Top, that's 3 minus x, and it goes all the way to the x-axis. So that's number 3. Okay, number 4, we're finding the area of region number 2, but this time I'm going to do it with respect to y. So those rectangles are horizontal rectangles. And this time, from bottom up throughout the region, and if you see this segment, the left end will always sit on the curve 2 square root of x, and the right end will always sit on the line 3 minus x. So one integral will do. Right? For this region to find the area, it's actually easier to do it in terms of y, because you only need to do it for one integral. But remember to write it in terms of y. So this one, remember, x is 3 minus y. And this one, x is y squared over 4. Bottom up, so from 0 to 2, function to the right minus function to the left. Okay, number 5, the focus is on region number 3. We need to find the area of region number 3, and this time we're going to do it with respect to x. So the setup for the rectangle is vertical kind. We need to find the height. And you can see throughout the entire region, the top function is 2 square root of x, and the bottom function is 3 minus x. That remains the same throughout the entire region. So we can do it with one integral. Going from left to right, we have top minus bottom. Number 6, we're finding the same area, but we're gonna do it with respect to y. So the setup for the rectangles, they are horizontal kind. For the bottom portion, we can go from the line 3 minus x all the way to the vertical line x is 3. But for the upper portion, we'll go from 2 square root of x all the way to the vertical line x is 3. So we have to do it in two integrals. Gotta break up this region into two pieces. Okay, so remember that this one, x is 3 minus y, and this one, x is y squared over 4, because we have to do it in terms of y. So area is the bottom portion going from bottom up. That goes from 0 to 2. Function to the right minus function to the left. The second part, the upper portion, it goes from 2 to, okay? So we gotta know that intersection here. It has x coordinate 3, but what's the y coordinate? If you're plugging 3 to the function 2 root x, the y coordinate is 2 root 3. So that's where we stop. Function to the right minus function to the left. Okay, so the first 6 problems, they're on areas. Is there any questions? Are we doing all right? Okay, so if no questions, then we move on to volumes now. Okay, so first is about cross-sectional method. All right, so again, the base will be these 3 regions. Okay, we practice. Number 7, the base of the solid is region number 1. And the cross sections perpendicular to the x-axis, right? So the keyword here, perpendicular to the x-axis. They can also say parallel to the y-axis, right? Remember, there are 2 ways to say it. Okay, so read carefully so you know what's the direction, right? Don't look at the y-axis, then you say, okay, do it in terms of y. You want to see the word, is it parallel to the y-axis or is it perpendicular to the y-axis? Okay, so you want to read it carefully. The base of the solid, so our focus is on region number 1. Whose cross section is perpendicular to the x-axis, so that means we cut it vertically. And all the cross sections, they are semicircles. Right, we practice this in the area part. We're cutting it vertically, so throughout the region, this distance can be formalized using just one formula. And what is that segment? That segment represents the diameter of those semicircular circles. And what is that distance? The diameter is equal to top minus the bottom. So that's the diameter. That's the length of that segment. Okay, once we know the diameter, we can find the area of that semicircle. So the area function is 1/2 pi r squared. Okay, r is half of the diameter. Okay. So when I grade your exams or forum quizzes, I noticed that yes, I require you communicate clearly the process, but you got to look at problem by problem, right? Some are like short answered questions you have to actually explain a little bit. Um, once in a while you have to have like a English sentence or two, right, to explain what's going on. But most of those problems, they are computational problems. So if you actually write it out properly, do it step by step, you don't need any English to explain what you're doing, um, because you get it, right? So if I have the picture of semicircle and the pink one, that's the diameter, and I write d is 3 minus x minus 2 square root of x, and when I try to find the area, I use 1/2 pi r squared, right? And the r 3 minus x minus 2 root x over 2. So you can see clearly what I'm doing. So I don't have to write a lot of English to explain what I'm trying to do. Right? Most of the computational problems, most of them does not require English to explain. If you show the steps, then people can follow, right? That's why you communicate clearly what you're doing, then people can follow your um, thought process. Okay, you're doing this, I see what's going on. Okay. But once in a while you may need to explain a little bit. And for this one, you can simplify a little bit. So that's my area function. And now my volume going from left to right. So from 0 to 1, and now you sticking the area function. Okay, so remember the formula says, right? And I'm trying to apply the formula, this concept. So that's the reason why I didn't jump to this one. Say volume goes from 0 to 1, and this. I communicated, how did I get this part? How did I get the area? Right? If I just threw you the last integral, the volume, you probably will ask me, how did you get the middle part? Right. So your job is try to not let reader ask the question, what's going on? What's that step? How did you get that? Okay, so that's 7. 8, the base is still solid, it's still region number 1, but this time the cross sections are perpendicular to the y-axis. Okay, so remember, they can say, right, instead of saying perpendicular to the y-axis, they can say parallel to the x-axis. There are two ways to say it. You gotta read it carefully, right? Don't just read half. Oh, x-axis or oh, y-axis. You gotta read it. The key word here is perpendicular or parallel. Okay, so perpendicular to the y-axis, so we cut it uh, horizontally, right, from our perspective, because it's perpendicular to the y-axis. So just like how we did the area, if we do it horizontally, we cannot formalize using one formula. We have to break it into two pieces. Okay, and this time they are all squares. Right, so they are all the same length, square. So S number 1 bottom part, we're doing in terms of y. So remember this x is y squared over 4. So the length is y squared over 4. So area function number 1 for the lower portion is y squared over 4 squared. And whether or not to square it out, that's up to you. You can leave it like this or you can square that out. And then the upper portion, the length of the side this time is going from the line 3 minus x to the y-axis. So that's 3 minus y. So the length is 3 minus y. So area function number 2 is 3 minus y squared. And volume, the lower portion from 0 to 2, so that's the lower portion. And then the upper portion, it goes from 2 to 3. Number 9, this time the base is region number 2, and so perpendicular to the x-axis. They're isosceles triangles with the base in the xy plane and the height, the half of the base. Find the volume. So just like finding areas, if we do it perpendicular to the x-axis, we have to break it up into 2 pieces. And we're looking at isosceles triangle. The height is half of the base. So base number 1, the left portion is 2 square root of x. And height is just going to be half of that. So area function number 1. Oh, my bad. Sorry. That's a of y. Please make the correction. Okay, so area function in terms of x, it's 1/2 base times the height. And the next part, base number 2 is 3 minus x, and height number 2, it's half of the base. So area number 2 is 1/2 base times the height. And in this case, the volume goes from the left portion, zero to 1, the first area function, and then from 1 to 3, and we're sticking the second area function. Number 10, the base of the solid is still R2, and this time we're doing it parallel to the x-axis. So that means perpendicular to the y-axis. And one formula can describe that length throughout the entire region. And this time we're looking at equilateral triangles. And what's that length? So remember, we gotta do it in terms of y. This side is 3 minus y, and this side is y squared over 4. So the length here function to the right minus function to the left. Okay, it's up to you how to find the area of an equilateral triangle. You can find the height, then do 1/2 base times the height. Or you can use the formula of 1/2 AB sine theta. Okay, so 1/2 AB, but A and B are the same. And sine of 60 degree is √3/2. Okay, and the volume now goes from bottom up from 0 to 2. And you stick in the area function. And then finish with dy. Okay, number 11. The base is region number 3. Cross sections parallel to the y-axis. They're isosceles right triangles. Okay, so parallel to the y-axis means perpendicular to the x-axis. So we're cutting it vertically, and if we're cutting it vertically, we just need one formula for that segment. And we're looking at isosceles right triangles with a horizontal leg in the xy plane. So that's one of the two legs of the right triangle. Right? So this leg is top minus the bottom, and the area function. And the height here is the other leg because it's perpendicular already, right? So it's 1/2 base times the height. And the volume will go from 1 to 3. And then you put in the area function. And finish with dx. In number 12, the base is still region 3, and the cross sections are parallel to the x-axis. That means perpendicular to the y-axis. So we cutting it horizontally, and if we cut it horizontally for region number 3, we gotta do it in 2 pieces. And the height twice the length of the side in the xy plane. So length number 1, the lower portion. Okay, so remember this line, x is 3 minus y. So that's 3 minus 3 minus y. Right, this is about communicating the process, right? If I just give you length number 1 is y, you're probably gonna ask, where did you get the y? Why is that y? But when I write 3 minus y, you know that I simplified that to get the y. So height is twice that. And area number 1 is y times 2y, which is 2y squared. And the next picture length number 2. Okay, so remember this segment, x is y squared over 4. Okay, so that's 3 minus y squared over 4. And the height number 2 is twice that. So the second area function is length times the height. And volume, bottom one, goes from 0 to 2. That's area number 1. Plus the top part. And we mentioned before, this intersection here, right, the y coordinate is 2 root 3. And we're sticking the second area function. Okay, so we did the cross-sectional method with 3 different regions and different orientations as well. So that's the first half of section 6.3. Okay, do you have any questions about these 6 problems before we move on? Okay, so if no questions, let's move on to second part of section 6.3, washer method. Okay, or disk method, because washer is basically disk method twice, right? And the 6.4 shell method. Okay, number 13. We want to find the volume of solid by rotating region number 1 around the x-axis using both washer and the shell. So first let's do washer. That's section 6.3, the second half. And this time, the region is region number 1. Axis of rotation is the x-axis. So when we rotate this around the x-axis, the cross sections, right, they are disks, right? You want to think about disk method, right? Really is the bigger volume minus the smaller volume. So the radius that's further away from the axis of rotation, so that's the big R. And then this is gonna be the radius that's closer to the axis of rotation. That's the little r. And throughout the region, it's just one expression for big R and one expression for little r. So one integration formula can help us to find the volume. And washer method rotating around the x-axis, meaning we're doing it with respect to x. We integrate with respect to x. So the big R in this case is 3 minus x. And the little r in this case is simply 2 square root of x. And the volume will go from left to right, pi times. So remember, it's Dick's method twice, right? The bigger volume minus the smaller volume. So that's the big R squared minus the little r squared. Okay, so that's washer method. Rotating region number 1 around the x-axis. So we're gonna do the washer method first, and then we're gonna come back and do shell method. Okay, so next problem. We're gonna find the volume of solid by rotating region number 1 around the y-axis. Okay, so this is still region number 1. Around the y-axis. Okay, so this time all the disks gonna be the horizontal kind, right? So we're gonna have two pieces, okay? And this time we are actually doing it disk method. Notice that there is no gap between the region and the axis of rotation. So in terms of washer, you can think of it's the big R squared minus 0 squared, because the distance between the edge of the region and the axis of rotation this time on the left, there's no distance, right? Because the left edge of the region is the axis of rotation, the y-axis, so there is no distance. Um, so the lower portion, the radius is, okay, so we gotta do it in terms of y. So again, x is y squared over 4. the upper portion okay, so for the line here, x is 3 minus y. And the volume goes, the bottom one from 0 to 2, pi simply r squared. The bottom part is the pink one. And the top part goes from 2 to 3. And the radius is the green one. Okay, 15. The region is region number 2, and we're rotating this around the line. Y is -1. And let's do washer first. Since the axis of rotation is parallel to the x-axis and we're doing washer method, so we're doing it with respect to x. And we have to cut the region into 2 pieces. So to find the volume, we need 2 integrals to complete the job. The first part, right, notice that from the bottom edge of the region and axis of rotation, there is a gap. So you know is a disk method twice, right? Pi r, big R squared minus the little r squared. Okay, so let's see. The left portion, this will be the big R because it's further away from the axis of rotation. And this part will be the inner R. It's closer to the axis of rotation. And for the second part, this will be the second big R because it's further away from the axis of rotation. And again, this is the inner R. Okay, so we can see clearly that in both cases, the little r1 and the little r2, no change. It's the same expression. It is a constant 1 because it's 1 unit away from the axis of rotation. Right. How do we find the big R1 and big R2? Okay, let's do R1 because R2 is done similarly, right? So this is what we're interested to find. I called it R1, and we know that this distance is 1 unit. It's constant. And this part is really 2 square root of x. So you can see clearly that R1 is 2 square root of x plus 1. Right. Okay, and similarly, our big R2 is gonna be from the green section, that's 3 minus x plus what? Okay, so this part we can simplify it. So when we simplify that, we get 4 minus x. And now we're ready to set up the integrals. Okay, the first one going from left to right, so 0 to 1, pi times big R squared. Okay, let me write it in pink. And then minus the little r squared. Let me write it in green. Oh, sorry. Little r is 1. The second integral will go from 1 to 3. And this time the big R, I'm gonna write it in green. Minus 1 squared. Okay, so next problem, we're gonna rotate region 2 again. And around the line, x is -1. And let's do washer method first. And since the axis of rotation is parallel to the y-axis, we do it in terms of y. Okay, and throughout the entire region, the green function is further away from the axis of rotation, and the pink function is closer to the axis of rotation, right? So the pink function, remember, we gotta do it in terms of y, so that's y squared over 4. The green one, it is 3 minus y. Okay, so how do we find that distance, right? Let me do a sketch. Okay, so this is what we want. That's the big R. Um, this distance is 1 unit. But this distance here is 3 minus y. Okay, so the big R is 3 minus y plus 1. That's 4 minus y. Similarly, the little r is going to be y squared over 4 plus 1. And this time one integral will do. Bottom up from 0 to 2, pi times big R squared minus the little r squared. Okay, so next one, we're rotating region number 3. Around the line y is 4. And let's first do washer. And because the axis of rotation is parallel to the x-axis, we're doing washer method, and that means we do it in terms of x. And throughout the entire region, the green function, this is always further away from the axis of rotation, and the pink one is always closer to the axis of rotation. So we do one integral. Right, so we want to know how to express this radius of rotation. And what we know here is this is 3 minus x, and the total distance here is 4. So from this picture, you can see that r plus 3 minus x is equal to 4. And big R is 4 minus the quantity 3 minus x. So that's 4 minus 3 plus x. So that's 1 plus x. And the little r can be found in similar way. So that should be 4 minus 2 square root of x. Volume it goes from 1 to 3 pi big R squared minus the little r squared Okay, I think we have one more problem on washer method. Still region 3. This time the axis of rotation is axis 4. Let's first do washer method. Since the axis of rotation is parallel to the y-axis, we gotta do it in terms of y. And this time we have to break it into 2 pieces. The bottom part from green function to the axis of rotation, that will be the big R. The small r will go from the vertical line to the axis of rotation. And the top portion, the big R goes from the pink function all the way to the axis of rotation. And the little r is still going from the vertical line at axis 3 to the axis of rotation. So from the picture, we can see that the inner radius for both the bottom and the top, okay, is the same, which is a constant 1. And how do we find the big R? And what we know here is this segment is 3 minus y, right? So remember, we got to do it in terms of y. And this total distance is 4 units, right? So from the picture, you can see that R1 plus 3 minus y is equal to 4. The blue plus green is the yellow or the gold color. So R1 is 4 minus the quantity 3 minus y. And when we simplify, we get 1 plus y. Similarly, the big R2 is going to be 4 minus y squared over 4. To find the volume, bottom portion goes from 0 to 2 pi big R squared minus the little r squared plus the second goes from 2 to 2 root 3 pi times big R squared minus the little r squared Okay, so that's the last one using washer method. Okay, so we rotate 3 different regions around different axes of rotation. We practiced washer method. So any questions about these 6 problems we just did on washer method? Okay, so now let's go back. Do the same thing all over again, but this time we're gonna do shell method. Okay, so region number 1 around the x-axis. Okay, so we're gonna rotate region number 1 around the x-axis, and this time we do shell method. For shell method, that's the opposite, right? We're rotating around the x-axis, we're actually doing it in terms of y. So think about the setup, right? What kind of shell we generate and how we uncut it and unroll it to get that rectangular slab. So when we're rotating around the x-axis, we generate a vertical kind of shell. When we cut it horizontally to unroll it, get a vertical rectangular slab. So for the lower portion, right, this is how we get the width of that shell or the width of that rectangular slab. And this is the top portion. And So with number one, for the lower portion, we got to do it in terms of y. Okay, so remember this in terms of y is y squared over 4. And the radius of rotation that's simply the y coordinate. That actually corresponds with the same expression for radius of rotation for the upper portion. It's just the y coordinate. So R1 is equal to R2 is simply the y coordinate. That will be the radius of rotation. It just has different range. The lower portion range from 0 to 2. The upper portion, the range will be from 2 to 3. Okay, but that distance, that vertical distance, the y value, is the radius of rotation. And with number 2, okay, so this line in terms of y is 3 minus y. So volume is equal to the lower portion goes from 0 to 2. 2 pi r times the width. In this case, it's simple. It's just W1. Y squared over 4. Plus the upper portion goes from 2 to 3, 2 pi r times the width. Okay, so that's shell method for finding the volume by rotating region number 1 around the x-axis. Okay, next we're rotating region number 1 around the y-axis. Okay, so region number 1 around the y-axis. And we're doing shell method. Okay, so around the y-axis for shell method, we are actually doing it in terms of x. Okay, so we have we're gonna cut the shell, the thin shell vertically and expand it horizontally to get the rectangular slab. So this is the height. And this is the radius of rotation. To find the height, that's the top function, 3 minus x, minus the bottom function, 2 square root of x. That's the height. And radius, that's simply the x coordinate. To find the volume, we go left and right from 0 to 1, 2 pi r times the height, right? So 2 pi r, that's the circumference of the shell when you unroll it. That's the length of the rectangular slab times the height times the thickness, delta x, right? Here, dx. If you can look up yesterday's lecture and visualize how to unroll that rectangular slab horizontally or vertically, right? It helps you to think about how to set it up. Okay, next we're going to rotate region number 2 around the axis y is 1. So region number 2, around the line y is -1. Okay, so this time we're doing it in terms of y. So we need to find the width of that rectangular slab. And this is the radius of rotation. Okay, so the width is easy to see. Throughout the entire region, the width can always be expressed by using the green function minus the pink function. Okay, so how do we express r? Right, so let's take a look on the side, perhaps, if you don't see it right away. Mhm. So we know that this distance here is 1 unit. And this distance here is simply y. So r is y plus 1. Okay, so we're doing it in terms of y. It goes bottom up from 0 to 2. 2 pi r times the width and dy at the end. Okay, next problem. We're rotating region number 2. Around the vertical line, x is -1. And we're doing it using Shell method. So for Shell method, rotating around a line that's parallel to the y-axis, we're actually doing it in terms of x. And we need to find the height of the rectangular slab. So that will be height number 1. And that will be height number 2. And this will be radius of rotation. Okay, so height number 1, it's simply the pink function, which is 2 root x. Height number 2 is the green function, which is 3 minus x. How do you find the expression for the radius of rotation? So this is what we want to know. Okay, and this is always 1 unit. And this distance is simply x. So in any case, the expression for R1 and R2 is the same, is x plus 1. To find the volume, we need 2 integrals. Okay, set up in terms of x. First one going from left to right, so 0 to 1, first portion, 2 pi r times the height. The first part, the height, is the pink function. Plus the second portion, the portion to the right, goes from 1 to 3, 2 pi r times the height. For the second portion, the height is 3 minus x dx. Okay, next we're rotating region number 3. Around the line y is 4. And we're doing it using shell method. Okay, since the axis of rotation is parallel to the x-axis for shell method, we're doing it in terms of y. And we need to break this into 2 pieces, right? Bottom part, that is width number 1. And top part, this is width number 2. And this is radius of rotation. Oh, my bad. Wrong axis of rotation, sorry. It's this direction. Okay, so let's look at width number 1. That's function to the right. Minus function to the left. So once we simplified it, we got y. Width number 2, function to the right, minus function to the left. And to find the expression for R, right? So this is what we need to find. And we know that this distance here is simply the y coordinate. And total distance is 4. Right, so from the picture, you can see clearly that R1 plus Y is equal to 4 units. Solve for that. Okay, the expression for R1 and R2 will be the same. 4 minus Y. To find the volume, bottom up, the lower portion will go from 0 to 2 pi r times width number 1 and the next one will go from 2 to 2 root 3 2 pi r times width number 2, that's 3 minus y squared over 4. Okay, so the last one, we're rotating region number 3. Around the line x is negative, oh, sorry, x is 4. For shell method. And we're doing it by rotating around the axis that's parallel to the y-axis. For shell method, we're doing it with respect to x. So this is the height. And this is the radius of rotation. The height is easy to find. Top minus the bottom. And how to find R, right? We can draw a separate picture to visualize it. right? So this is what we need to find, r, but this distance is x, and total distance is 4, right? So we can see that x plus r is equal to 4. So r is 4 minus x. So one integral will do. Volume goes from 1 to 3 to pi r times the height. Okay, so that's the last one on shell method. So again, the best way to remember the shell method is actually to go over the portion when I derive the formula. I have some drawings. If you're able to visualize that one sample thin shell and how you cut it and unroll it, right? If you can make the connection of that, it's very easy for you to set up the integral. Otherwise, the shell method can be confusing. So my recommendation is go back to the basic definition in the standard position, visualize that thin shell, how you generate the thin shell, and how you cut that to expand it, to unroll it to the rectangular step. Once you can visualize and make connection for the standard position for shell method, and when you shift it the axis of rotation, you're gonna be okay. Because you're not gonna be confused. Are you gonna do it in terms of X or in terms of Y? How to unroll the shell and which part is the uh, radius of rotation. So so that's 6.4 shell method. Any questions about these six that we did for shell? Okay, if I have any typos, let me know too, right? I'm talking and writing, and it's very possible that I make a careless mistake somewhere along the way. And you're pretty sharp, so let me know. Okay, so looks like we're good. And exam 4 will be tomorrow, so we don't have lecture. You study and then do your last exam. And just a reminder, today, Wednesday, make sure you finish all the CLOs, all right? Because that is absolutely required. It may affect your eligibility for a C or better grade. But those CLOs are the easy ones, right? You even get multiple attempts. So I recommend you get 100% um, to earn extra credit as well. So in any case, you want to finish all of those and make sure you get at least two correctly, right? The bottom line, you get at least two correctly to meet the eligibility requirement. Go over the last quiz solution, right? That's for you substitution. So for tomorrow's test, when you do integration, make sure you communicate clearly the process so that I know exactly how you simplified and which formula you applied. Okay. So follow the class example, follow the quiz solution so you know how much to write, right? You don't have to write a whole bunch of English to tell me what you did, right? I mean, that's good. That helped me to understand, but to save you time of writing, if you reference class examples, so you know exactly how much to write, right? I'm not asking you to write um, everything in English and too much of details, okay? Do you have any questions before we go? Because this is our last class meeting. Okay, if no questions, I wish you good luck and hang in there. Tomorrow is the last day, and then have a good summer.